Hello, everyone, and welcome to our conversation today on a new SMPC-based system or protocol and how Worldcoin is using it for biometric template protection. As usual on the space, we've got a great set of guests I think you're going to really enjoy hearing from. And so first of all, I just want to thank everyone that joined, especially our guests and especially everyone listening. I know we've got a lot of people on already, and we'll have a lot of people joining as the space goes on. And then we always record these and make them available afterwards. So a lot of people will be able to listen to the recording. But yeah, just to get everyone going, this development that was announced today by the Worldcoin Foundation is something that's been in the works for quite some time. It's been a research area for us since I've been involved in the project for about 1.5 years now. And we've explored different avenues for what ultimately we're leveraging SMPC for. But just to catch everyone up, if you didn't see the announcement earlier, today the Worldcoin Foundation unveiled a new, what we consider state-of-the-art secure multi-party computation protocol, or SMPC, as you commonly see it abbreviated, for core service within the Worldcoin system, which is the uniqueness check, which we'll get into talking about in more detail in a bit. A key, a key aspect is everything we do on the protocol side is open source, and this SMPC-based protocol is no exception. So it is open source. It can be used by anyone, any organization for any reason. Typically, SMPC is used to protect data in some fashion. So it's a great protocol for protecting data, and in particular, biometric data. And today we're going to get into the details of SMPC and biometric template protection. And so there's a lot to unpack, but the key point of all this, or the summary, is essentially today, what the Worldcoin Foundation is doing is announcing the way it's leveraging cryptography to take World ID privacy and Worldcoin privacy to a whole new level that, as far as we know, has never been done on this scale. Before we go any further, as I mentioned, we've got a great set of speakers. I want to take just a moment to allow them to provide like a brief intro for themselves. So I want to start with Remco. Remco, I believe you're on the call, so you want to kick us off?
Yes, hello. So I'm Remco. I'm at the Worldcoin Foundation. I've been with the Worldcoin project for, almost 3 years now. Kind of joined when the org was mostly done and we started working hard on the protocol side of things. And I joined as the head of protocol and now at Foundation. And as such, I'm like always trying to push us to become more trustless and more decentralized. And the uniqueness service, as we'll see, was always a very challenging aspect of that. So I'm super excited about the breakthrough that we'll be talking about today.
All right, very good. And Philipp, I believe you're on the call as well already.
Yes, I'm also here. Yeah, thanks for having me. Philipp, Sippl, my name. I've been part of the project since the very beginning, so 4.5 years. Now also part of the Worldcoin Foundation as Remco. They're director and also overseeing a lot of engineering, but also very involved in a lot of the engineering, especially specifically related to the protocol and blockchain side. So also the SMPC protocol.
Right. Very good. And Lukas, I believe you're on the call as well.
Yes. Hi, everyone from my side as well. My name is Lukas and I'm the CEO and co-founder of the TACEO, where we're focusing on encrypted computation using SMPC. Before that, I was a cryptography and privacy researcher at the Graz University of Technology. I'm really excited to be here today and look forward to discussion to this really special use case.
All right, very good. And I see we also have Bryan with us as well. Bryan, would you like to introduce yourself?
Yeah, absolutely. Hey, everybody. I'm Bryan Gillespie. I'm from a theoretical mathematics background, and I got into cryptography a few years ago. And I'm a research cryptographer now at a small consulting group called Inverse Tech, which focuses on privacy tech and privacy in the open internet. And we've been working with Worldcoin on this project, doing research on biometric template protection and ways that it can be applied for Worldcoin's application since around September. It's a really incredible project. Excited to be talking here.
All right, great. As I mentioned, we have a great set of speakers, and as typical on these spaces, they're all incredibly humble. But I cannot tell you the knowledge and like intellectual bandwidth this group has, like some of the best cryptographers I've ever known and worked with. And it's just amazing to just watch them work and be able to tag along with them and try to keep up. Okay, so before we get going any further, we always try to save some time at the end for questions. So if you have any questions at all that come up during the space about anything we're talking about, SMPC, biometric template protection, et cetera, just drop those in the Twitter thread and we'll do our best to get to as many of those as we can at the end. But like I say, we always have some flexibility toward the end to get some of these answered. And usually we answer some as it goes, but we really love getting questions from the audience. So feel free to just add those in. Okay, so let's kind of dive in. I mentioned at the outset, we're using SMPC for something called biometric template protection, which clearly means that Worldcoin uses biometric templates in some fashion. So I'd like to start with Philipp, who, as he mentioned, is one of the founding team members. He's been here since the inception of the project. So Philipp, you want to give us just an overview of how Worldcoin uses biometrics and just kind of kick us off with that basic level set?
Sure. So very fundamentally or importantly, the problem that we had to solve is twofold, right? We have to solve the problem of humanness and uniqueness to actually be able to issue a WLD such that you're not able to game the system and get more of them, but you should also not be able to game them, but also not be able to get more of them as a real person. For that purpose, we sought out multiple different options. The only one that was feasible in our eyes on a large scale is through biometrics. And for that purpose, we also had to actually build a custom hardware device because none of the existing hardware had the required accuracy in terms of biometric performance, and also nothing was really like in this form factor could be used everywhere in the world in a somewhat mobile way. So we built out this specialized hardware device to be called the Orb. And fundamentally, its job is really to do those two things. So it verifies your humanness, which it does by pretty much taking a bunch of signals from your face, RGB and different wavelength images. And this is fully done locally on the Orb. And this is not quite enough, as I mentioned. You still need a signal about the uniqueness, and you have not done this as a real person before. And for that purpose, the Orb produces something that is called an iris code. And this is ultimately then used not only locally, but actually it needs to be used remotely, right? Because there are more than one orb out there to deduplicate or check that this user actually has not signed up yet. And importantly, it's also not only used once, right? But you have to retain this iris code because a user could come back later, and you need to want to keep this uniqueness over a longer period of time. And now the whole SMPC announcement, or like the whole protocol, is about exactly that part: how to store and use this iris code in a secure and private way. And I think maybe Remco, you can dive more into the details there.
Yeah, so we're talking now about the uniqueness service, the thing that where the Orb produces this iris code in like a trusted environment, then we need to make sure that this iris code is actually unique. That's the job of the aptly named uniqueness service. So the thing it does is deduplication. And this is distinct from the more common use case of authentication for biometrics. Like people know, for example, your laptop that unlocks with a fingerprint or your phone that unlocks with a face. What happens there is that you just make sure that the user is indeed the user that the device is familiar with, which is an easy problem. What we need to do is a little bit more complicated. We need to make sure that the new user isn't actually secretly one of the users that already signed up before. And for that to work, you need to compare the user against all users that signed up before. So instead of doing a one-on-one comparison, we need to do a one-on-n comparison, which is a quadratically larger problem. And this is the root of it's a big chunk of the technical challenge here, just the scale of doing this quadratic operation and making sure that users are not trying to sign up multiple times by deduplicating them.
Right. Very good. Yeah. Thanks, Phil and Remco for that. And it's a distinct difference, right? Deduplication and authentication. And Philip mentioned iris codes, which an iris code is technically called a biometric template. So that's where that term came from that I mentioned earlier. And it's important to protect those clearly, just like any data that you have. But I want to take a bit of time and talk about biometric template protection. So we understand kind of how Worldcoin uses biometrics, but let's talk more about that specifically. Bryan, and could you just give us an overview of biometric template protection, what it is and why it's necessary, those kind of things?
Yeah, absolutely. As Stephen said, the iris code is called a biometric template, just another word for the kind of compact representation of the data that is derived from the iris sensor readings. Now, this data can be thought of like a signature or a password that each individual has. And in particular, it's something that can't be easily changed. And so it's really important to make sure that even in the case that somebody gets access to this data in some bad way, they can't rederive the biometric information that underlies the data. So there needs to be some way to obfuscate or protect the biometric template in the representation that you choose. And so this is what the field of biometric template protection is about, is finding good ways to represent this biometric data so that you can't rederive the actual biometric information in a usable way or correlate it with biometric readings in some other system, but it still allows the comparison that needs to be done for this deduplication process to take place. So there's a variety of different ways that biometric template protection is accomplished. The whole research literature of different ways for different biometric sources in general. There's face recognition and fingerprint recognition. And iris recognition, of course, is one of the most accurate versions of biometric authentication or user recognition. So that's why it's being used by the Worldcoin, which has very large, high accuracy requirements for the comparisons that they're trying to do. And so a few of the approaches that we've investigated at various times are good in some contexts, but often not in the context of Worldcoin, which has kind of a trifecta of needs, which are high privacy, really high privacy concerns. It's one of the top priorities of the designs that we're looking at, as well as performance. You need something that can perform well over a fairly large database, and also high accuracy. Again, because of the kind of quadratic nature of the comparisons that are needed for deduplication. And so that trifecta of characteristics really ends up being a problem for a lot of these biometric template protection methods that have been explored in the literature, just due to the fact that the contexts in which these methods were designed are aiming for different applications, where you have a smaller database or you have a different setting for how these templates are being compared. So a few of the kind of dead ends that we explored include there's something called locality sensitive hashing, which is a method of comparing data by using a bank of hash functions that provide some kind of output hash function overall that changes gradually as you go through the space of possible input points, which works well in certain contexts. But what we found was that in particular for the high dimensional data of iris codes, which are on the order of thousands to 10,000 bits of data, it wasn't accurate enough. Or in order to get the accuracy that you needed, it was fairly expensive to do the comparison operations. Another method that really showed a lot of promise is something that's called fuzzy commitments. And it uses a combination of cryptographic hash functions along with error-corrected codes in order to produce a protected biometric template, which has the really nice property that you can't decode anything obvious about the biometric template unless you have as input a biometric template data point that is very close to the original biometric input. And so it showed a lot of promise. It looked like it had some good privacy properties and seemed to work very well in terms of performance. But what we realized is that actually there was some difficulties that we couldn't get around with the privacy characteristics at the end, because the representation as a template, as a protected template, includes what's called some helper data. And we realized that helper data actually reveals some information about the underlying iris code. It's not information that you can retrieve like specific bits of the iris code, but what it is actually, if you're into linear algebra, is it's the projection onto a large linear subspace over the binary field of the binary input of the iris code. And the amount of data that it revealed in that setting, it was not obvious to us how that could be applied in a nefarious way, but it just didn't make us comfortable as far as being truly a private solution for what we were trying to accomplish. In the end, what we ended up realizing was a good approach that we could work with was simply turning to advanced technology in encryption. So there are some very useful and viable now techniques in cryptography right now that allow computation over data that's stored in the encrypted domain. So this is This is in particular the two techniques that are most well known are homomorphic encryption and secure multi-party computation. And the idea is that the data is encrypted or fragmented in some way so that no part of the data can be used to actually retrieve the underlying biometric values. But then in the end, you can do the computation and retrieve just the output of the query, a yes or no on whether two templates match using cryptographic techniques. And I think that Remco may go into some more detail in just a second about how this applies in Worldcoin's current design.
Yeah, thank you, Brian. That is an excellent overview and background on biometric template protection and some of the methodologies that have been used and are being used. And again, it comes back to the use case. Is it authentication? Is it deduplication? Is it something else? But that's a great segue into SMPC specifically. So let's dive into that with the background on how WorldCoin uses biometrics, what biometric templates are, and the different protection methodologies. So let's just jump straight into that. So Remco, I'm going to start with you. Then I'm going to bring Lukas in as well. But just tell us what SMPC is, explain how it works and things of that nature.
Yeah, so like Brian said, there are two ways really of doing a computation over data without actually knowing what that data is. One is FHE, where a single computer can do it, but then you have a decryption key that this computer is not supposed to know that you can use to decrypt the answer. The other is secure multi-party computation, where you have multiple computers that together do a computation, meaning that each has some local data and can communicate with the other participants. And they follow a little protocol together. And the end result is that each of them now knows a so-called secret share. And when you get all these secret shares together, you can reveal an answer, an output to the computation that you're trying to do. So the basis of at least the SMPC protocols that we're looking into is this secret sharing scheme. The way secret sharing works is that kind of like encryption. You start with raw plain text data that you want to store securely, and then you move it to an encrypted domain to encrypted shares. But instead of with regular encryption, where you end up with a secret key that is kind of a fixed size of about 256 bits, and then your data encrypted the size of your original data, you now end up with multiple pieces of data, each of the size about your original data or even larger, but you don't have a decryption key. Instead, the pieces of data collectively form their own decryption keys. You need to bring all of these pieces of data together in order to recover the original secret. There's some variations on this where you can have like a threshold mechanism in there where you could, for example, create 5 secret shares, and then if you have 3 out of 5, you can recover the secret. This is really good, for example, storing the private keys of your wallet, where you want to store it in several, let's say, safes or houses or secure locations, such that if, like, I don't know, maybe 2 places get broken into and your private key is still safe, maybe one burns down and you lose that one, and you can still recover your private key. It isn't until, if you ever do need to recover your key, you simply go to 3 of those locations, take those secret shares, combine them, and now you have your private key back again. So that's one scenario where I think most blockchain people have seen secret sharing before. Now that's only a way to store secrets, but then it turns out there are actually really clever algorithms and protocols that you can use so that you can not only store these secrets, you can actually do any kind of computation over them. And as it turns out, this includes doing iris code matchings like we need to do for the uniqueness service. This to me was a surprising result. I've heard of SMPC protocols before, and every time I heard of them, they talked about something called Gauss garbled circuits, which is actually something entirely different. And maybe this is a good question for Lukas. Why haven't I heard of these linear secret sharing scheme based secure multi-party computation protocols before? And can you just tell me a little bit more about the recent history of them?
Yeah. So I can only guess why you didn't hear about the linear secret sharing schemes, but why maybe Gauss garbled circuits are so popular is one reason is that it's one of the earliest protocols that applied multi-party computation that really laid some of the foundational work in this field in the 80s. But I think the popularity of garbled circuit really stems from how they were first used to illustrate the potential of MPC with a very well-known problem, which is called the Yao's millionaire problem. So this is the classical example which every cryptography student gets to know. It's the 101, and it's like Alice and Bob, both are millionaires and want to find out who is wealthier without giving away how much money they actually have. And this was a catchy problem which stick with the people, and because it had the same name as the circuit, this was the first go-to if you're thinking about MPC and concrete protocols.
All right. Very good. Yeah. Appreciate that background. Lukas, we talk a lot at the project about zero knowledge proofs. So just basically, could you kind of just highlight the difference? And I know it's two totally different things. So it's like saying, what's the difference in an apple and an orange? But could you just highlight the differences of ZKPs? Because I just want to make sure that we draw that distinction.
Yeah, maybe I can go first here. So for me, ZKPs are a way to do a verified computation or to prove to somebody else that you know some input data, some assignment, some secret without revealing it. And multi-party computation is really all about collaborative computing. So if you have, like Remco mentioned, secret sharing your data, or you want to compute data cross organizations or with other users, then MPC comes into play.
Okay, excellent. And one more thing I want to touch on before we move on from SMC itself, before we talk about Worldcoin and SMPC in particular, is, and I think, Lukas, you're probably best suited to answer this one as well. What are some of the recent advancements in SMPC? So SMPC, again, just for background for everyone, has been around for quite some time. It has a ton of applications, but what are some of the more recent advancements, which I know that your team's been involved in working with? What are some of the more recent advancements?
Yeah. So the biggest advancements, especially for the use case we're talking today in the MPC in the last years, in my opinion, came from the demand for privacy preserving machine learning. From being easy to prove on the paper, the protocols like in 2000s and 2010, the protocols got more optimized towards the machine learning approach and towards native implementations on CPUs and GPUs, for example. And another great improvement, which we saw, was a paper called EPI3, which allows you to easily switch between different MPC protocols in a machine learning setting. As most people know, you have different computational tasks once you're doing machine learning. And it was always clear that different MPC protocols perform better on, for example, matrix multiplication, the other ones on nonlinear computations. And so this was I think in 2017 or 18, the first paper that really formalized how you can switch between those protocols in a very efficient and, most important, and a secure way to leverage the pros of these protocols.
All right, very good. So shifting gears, let's talk specifically about the SMPC protocol or system, whatever you want to call it, that's been implemented for the Worldcoin project. So what's unique about it, and why is this such a big deal? So I want to start with Remco and Philipp. They were heavily involved both on the Worldcoin side and SMPC side, and just talk about how Worldcoin is using SMPC. We'll start there.
Yeah, I can start here. So what is unique to us is that, like I said, we've been looking into all these different solutions for quite a while without finding anything that we were particularly enthusiastic about. And this is clearly a very good protocol, and it is only through these applications of this ABY3 style tricks where you have different SMPC protocols that each cater to a particular use case. Like one we use for dot products, a different one we use for distance comparisons, and so on. It's only with these relatively recent developments that you can piece together an SMPC-based protocol that meets all these security and performance requirements that we're looking for.
Okay, very good. Philipp, anything to add, or anyone else want to chime in?
Yeah, I guess what is to add there is specifically for our use cases is the scale always, right? So I think there were probably some schemes that you could have applied on the smaller projects, but we always come with very high demands in terms of scale and like how many users the system needs to support. And yeah, this leads to, I think we mentioned in the blog post, to thousands of CPUs involved and terabytes of memory. So also the gap between theory and implementation is sometimes decent.
It's incredible. So Philipp mentioned when he gave his description of how WorldCoin is using biometrics and biometric templates, for example, talked about the iris code. Remco, back to you on this. WorldCoin's clearly using SMPC now. And, kind of high level, what's the difference? Like before we were using iris codes, we've still got to use biometric templates for the deduplication use case. How does SMPC figure in specifically to that use, that processing of iris codes for the dedup use case?
Sure. In the before setup, which is according to all the best practices known before this line of research, which you essentially end up with is a very well protected encrypted database. But if for each matching, you still need to decrypt the record that you want to match against. And what this SMPC allows you to do is get rid of that entirely. Like you can literally delete it and replace it instead with this SMPC setup where you now have these encrypted shares that stay in two separate locations, and you never need to decrypt them in order to make a matching. I think that's a simple explanation of what this SMPC unlocks. Now, the way this works in practice is that the iris codes is basically a handling distance comparison, a little bit more nuanced, but it's a good first approximation. And what we did is we convert that to a dot product, which is a more algebraic operation, a linear operation. But that is one that is also used a ton in machine learning. So we could use the really efficient algorithms that have been developed for the machine learning field and apply them to this dot product in order to get a very efficient SMPC implementation for the iris code.
All right. Excellent. No, perfect explanation. Let's see. So Lukas, we did talk about already the advancements in SMPC for machine learning, which then was able to be applied in our situation or the WorldCoin situation to iris codes for the uniqueness check, comparative processing, whatever you'd like to call it. Anything else or anyone else on the call want to chime in on anything related to WorldCoin and SMPC before we kind of move on to maybe the future side of things?
Yeah, I think Remco did a really good explanation about how machine learning or the machine learning techniques applied here, but I just wanted to re-highlight how ambitious this was, like when I think first talked to Philipp back in last summer. So taking back to Bryan, the fact that what you want to solve with this use case, privacy, accuracy, and performance, I think it was really clear to us that privacy and accuracy could be achieved with MPC very easily. But once we got hold of how ambitious the project is and how many users it should scale, I haven't told that anyone, or Philipp or Remco, but we were kind of the edge on quitting on this use case because we thought there is no way you could make this possible. Gladly, we did spend a few nights then finding some new angles, and now, working together for a couple of months. I think we have made a lot of progress that will also spill beyond these use cases. So, for example, into more general machine learning use cases, which involve MPC. So I'm really glad that it worked out in this way.
Yeah, just to give a little bit more color here, our optimization efforts have resulted in issues being submitted and PRs being merged in both LLVM and CUDA.
Right. And for those that, so I just cannot let this pass because this is so cool to me. What is LLVM for people that may not know, Remco?
Okay, good. So LLVM is basically what every modern compiler built on. It is the thing that makes Rust such a fast language. And we actually found is that for Amazon's compute optimized CPUs, it wasn't doing an optimal job in generating instructions. So we actually figured out why that was the case and submitted an issue for it. And to their credit, they fixed it within hours. But that shows you that we're just pushing the edge so much that we found corners of the compiler where we could beat the compiler due to misconceptions in there. Similarly, on the CUDA front, we were also, Philipp can tell more about that, but we also found that in their matrix multiplication routines, there was simply a precision error that was entirely avoidable. And after we flagged it, they did indeed fix it. And we got the accuracy of their matrix multiplications to the level that we need to implement the protocol that we want.
Okay, very good. So that, and what I wanted to highlight there is that's the level of research and depth that the team has gone to come up with this like incredibly optimized protocol. And to Lukas' point earlier, you kind of begin to scratch your head a little bit and go, can SMPC scale to this level? And by the way, it's a great segue into the next section where we're going to talk about the future of SMPC and biometric template protection. Worldcoin has about 5.3 or maybe a little over people that have been verified as an orb. So unique humans in the identity data set, if you will. So the scale challenges of just that are enormous. Our scale target is ultimately 1 billion. So you can imagine the challenges that we'll face going forward, which is, again, a great segue into the future of SMPC biometric template protection. So let's just head into that. We're always, as Bryan mentioned, like one of our, kind of one of the matrices, if you will, that we're always evaluating like new protocols, cryptography against is one, it's got to be highly performant, and two, it's got to be privacy preserving at the utmost scale. As we move into scaling up for 1 billion users, continuing to evolve the SMPC protocol and others, let's just talk about that. Let's just talk about the future of some of the things as we know it today. Some things subject to change, of course, as we learn more. But Remco, you want to kick us off and just talk about some upcoming work?
Yeah, I highlighted it already a bit earlier, but so what we have developed is a whole protocol that provides an enormous amount of privacy end to end that will be rolling out in phases. And this was just what we announced today was just the first step towards that. And I think the end result, I'm not going to spoil all of it, but I think the end result will actually be really impressive in how much we can achieve our goal of just full trustless self-custody of all the data to the user.
Yeah, I totally agree. Like we were just chatting about that actually earlier today on a call, you and I, and it's incredibly exciting, like the vision. But yeah, we'll have many more Twitter spaces between this point and that point, but it's incredibly exciting. And Philipp, just continuing the thread, what does this new work, this upcoming work mean for the future of Worldcoin privacy?
Yeah, I think also what is interesting to mention here is that we now talk about MPC or SPC, but it's all in addition to the zero knowledge proofs that are already existing and every user uses to actually use their WLD. So this is really another level. And I think this is a good mental model also for the privacy of WLD in general, that there are multiple levels and you'll go to a great extent in increasing those levels. And so SMPC is one, but there are, I think, many other different levels that we can build even stronger privacy on. But yeah, so that's the ultimate goal.
All right, very good. And Lukas, you want to chime in there? Future version of the Iris Code protocol, maybe?
Yeah, so I'm really excited, but it's still up the sleeve. So as usual, research is a bit ahead of than the engineering tasks. So the future upgrades to the protocol, as we, at least in the research, have planned, expand this SMPC environment to also protect the query iris codes as well as the associated iris masks. And in the next edition, also protect the distances between the queried iris codes and the iris code database. So in the end, the server only gets a binary response if, yes, this is a new iris code, or no, this is not a new iris code. And on another dimension, really looking forward to having these, what Remco already mentioned, and where also Philipp is the expert, GPU implementation of the most computational heavy parts, which I think will get us in the direction that we can fulfill this growth target, the very ambitious one from Worldcoin that you, Stephen, already mentioned.
Oh, very good. And Bryan, you want to close this section out? I know you and the team at Inverse have been doing a ton of work. I mentioned earlier, we're at 5.3 million roughly users. verified users, but we want to scale to 1 billion. So you want to talk to us about some of the things that you and your team have been researching in particular about how we achieve that scale.
Yeah, absolutely. So the whole trade-off here is that SMPC provides a really impressive level of privacy and extra security on top of the computations that Worldcoin already needs to accomplish for their deduplication engine. But it comes at a cost. There's no free lunch. And the cost is that the computation is heavier. It's a bigger computation. And so the other axis, aside from accelerating the underlying SMPC protocol and GPU acceleration and all kinds of crazy things, teams that are working on that are doing an excellent job. The other way of approaching it is to reduce the overall plain text computation that goes on. So all of this is like some computation that's happening in the encrypted domain. So the first approach that is looking to be implementable in the short term is a filtering phase, which starts with a lower resolution encoding of an iris code, which has a trade-off, which is it's smaller, and so it's easier to compute over, but it's smaller, so it has less data, and so the accuracy is less effective at actually determining when two iris codes are matching. So that is probably something that would be not difficult to implement in the short to medium term in the system. We have a more sophisticated trick up our sleeves that we're looking into, which is using a method that's called a proximate nearest neighbor search over a type of data representation of the database called the hierarchical navigable small world graphs. So this is a really interesting find. It's a technique that's used in machine learning applications, actually. And so if it's possible to implement this HNSW approximate nearest neighbor graph search in an MPC setting, in a shell, which is privacy protected because of the SMPC protocol, then you start to get to scaling that actually works at the billion iris code level. And it has a lot of promise for being something that will work in the long term for this system.
All right. Very good. So, clearly, and this is, so I get to do a lot of really interesting things, tools for humanity. And of course, we're developer on the Worldcoin project. But this to me is like some of the most fun, most interesting things. And when I say this, just this whole progression, and which led to SMPC, all the different avenues that were explored, the different things you get to learn. And quite honestly, the project pushes the limits of what's been accomplished in so many different ways. And this is just another great example. Yeah, we're getting close we're going to move into questions now for a few minutes. We've got a few from the audience. One quick note before we get to those. When I said we announced today, it's actually on worldcoin.org/blog. You can go find a really great write-up on the SMPC protocol. So if you want, more details than we've provided here today, you can kind of get it in a very contiguous flow and learn more about it. I would also like to caveat the discussion today. I mentioned at the beginning, we're going to keep it pretty high level. And this team being high level, just so you know. We got into to some great detail around technologies, but that's just the fun of getting to hang out with folks like this. Anyway, so let's move into questions. We've got a few. So the first one we have is, it says, does that call for new captures? And my assumption there means, okay, for us to use the SMPC protocol now versus what we previously used, do people have to go, visit an orb again for a new capture? So I'll just toss that out. Philipp or Rem, would you like to respond to that one?
Yeah, it's not needed because pretty much we were able, or like due to having the iris codes beforehand, we were able to pretty much upgrade them to the new system. And yeah, so nobody needs to go back to an orb for the purpose.
Right. Yeah, that's been always one of the drivers of use cases. But yeah, nope. So the answer to your question, just like Philipp said, is no, you don't have to go back. No one has to go back for a new capture. We've got a second question. It says, I'll just read it as is. Homeomorphic encryption is data heavy. To Brian's point earlier, anytime you start doing something with encryption, you're adding, quite a bit of overhead in most cases. But homeomorphic encryption is data heavy. Have you considered an irreversible token where data is removed / obfuscated and noise, et cetera, is added? And then a comment, it's technology that's been used for a while with biometrics to preserve privacy. Has this been considered? And I'll just toss that out for anyone that wants to respond to that.
Yeah, I can say a few things about that. So the answer is yes. We have looked at homomorphic encryption as a way of accomplishing these computational tasks. And it's actually still on the plate as a viable technique for various aspects of this computation stack. It turns out that there's some interesting integrations between SMPC techniques and FHE techniques. There's some give and take where you can use one technique to accomplish something for the other technique. It turns out that there are some very nice optimizations that you can do, especially in techniques using what's called the ring learning with errors assumption. The underlying data objects have some nice properties that allow computation of inner products that are used for the iris code comparisons to do reasonably well. SMPC, and it happens, tends to be a little bit faster in practice, which is one of the reasons why we're moving in that direction currently, but it's still something as a technique that's on the table. And we have found ways to enhance, we believe, the state of the art on homomorphic encryption as a method for doing these comparison operations as well.
Okay, very good. I believe that is all the questions that we have. We answered a few of them, of course, as we were going through the space. But yeah, with that, we'll wrap up. We're a little bit over our target time, but still well within the hour. Once again, I just want to thank everyone that joined us for the space live and that will subsequently listen to the recording. We really appreciate the interest in Worldcoin and the project. Special thanks to Remco, Philipp, Lukas, and Bryan for taking the time to hop on the space today and talk in detail about this phenomenal announcement and advancement. I always love getting to hang out with these folks, which I get to do typically on a daily basis anyway. But hope everyone has a good rest of your day and look forward to catching up with everyone on the next space.